Welcome to a continuation of our System Devices 2 networking lectures. So lecture 4A, again, part 2, the lecture wouldn't die. And those of you who have done any networking before won't be surprised that these two lectures are taking a long time to go through because TCP and IP are big protocols. There's a lot to go through. So we don't want to rush these protocols because they are the fundamental building blocks of any network. So you need to understand these two protocols in a little bit more detail than perhaps HTTP, SMTP, DNS, etc. They're still important protocols, but they are not backbone protocols such as TCP and IP. These are the ones you need to know. So for these two protocols, we have part twos. More fun. So at the end of the last lecture, we were chatting about how we're going to build our network, and we saw that it could be built from hub switches and routers. And we raised the question, what are these? They all look very similar, if I'm being honest. They're kind of boxes with ports on the front or the back, which you shove cables into and you can connect up your networks. Typically, as we saw in the first lecture, we're arranging things in star topologies. And by connecting these network resources together, we can form our desired networks. Okay then, so we're using either IP version 4 or IP version 6. So in these diagrams from now on, looking at IP version 4 examples, we need to route those packets across the network using those IP addresses. And to do that, those packets will be passed through hub switches and routers. So this raises the question, what's the difference? So the hub you can think as a layer 1 device, so a repeater. So it looks the same as a switch, but electrically, think of it as just a wire. It just boosts the signal coming in and will transmit it across all the connections. So it's no different to that 10-base-2 coax cable we saw previously in some respects. You'll still have collisions. You've still got one collision domain there. So to handle that one, we have to develop protocols to detect when multiple things transmit, cause that collision. So you get carrier sense, multiple access, collision detection algorithms. Basically, if two things try to transmit at the same time, you stop transmitting, wait a random amount of time, and then try again. I'm not going to go into too much detail on that one because hubs aren't used anymore, really. So if you want more information, do follow that link in the slides. So if hubs aren't used, what do we use? We use switches. So the one in the lab on our Raspberry Pi system is a layer 2 switch. As I say, it looks exactly the same as a hub in many respects. I guess you can think of a switch as a clever hub. It can work out who is connected to what port. Now that's... And when I'm talking about switches and routers, when I say port, I don't mean port in the sense of TCP and UDP. A port is a socket. So where you plug that cable in on a switch, that's called a port. Not confusing at all. So the different things connected in each port, the switch can detect using the MAC address, which I haven't looked at quite yet. So when you're plugging your cables into your switch, into the ports, you connect your hosts to the switch. The switch can learn by looking at the Ethernet addresses of each host who is connected to what port. So as those packets come in, it will look at those MAC addresses, it will look at those layer 2 addresses and work out where that packet should go, what port it should go out of from the switch to get to where it needs to get to. Unlike a hub, if you had a packet coming in on one port, it would just retransmit them out onto all the other ports, effectively broadcasting every packet to every host, which from a security point of view is not a good idea. Another fundamental difference between a hub and a switch is fully duplex, so it can transmit and receive at the same time. And now, because the switch doesn't retransmit everything on all ports, we now have effectively multiple collision domains. So we're splitting up our network. So at this stage, hubs and switches, we haven't looked at those in detail at the moment because they're lower down on the stack. So you can just consider those as the things that glue computers together. So if we go back to our diagram here, you can see I have multiple machines connected to a switch. So this glues them together into that subnet so that the switch can then talk to the router. And same for hubs. So it's a way of connecting together computers onto a local network, onto your local area network. And then if they want to talk to other networks, they have to go to this router in the middle. So at this stage, don't worry about hubs and switches too much, because in this lecture we're looking at layer 3, the network layer. We don't need to concern ourselves at the moment with these devices. What we're interested in is the router. So our router is the thing that routes packets across networks. So a router looks at IP addresses. It'll have a set of rules that it uses to determine where stuff should go. So that can be static, so hard-coded routes within the router, or dynamic, in the sense that it will get that information from routing protocols. So OSPF or RIP, which we'll look at later, are routing protocols that allow the routers to talk to each other, to tell each other what networks they know about. But fundamentally, what does a router do? It looks at the destination IP address, and from that it decides what network it should forward that packet onto so that it can get to its desired destination. Some other terms, bridges and gateways. So bridges for me are a way of joining things together again. So I used to see these a lot when we had our older networks, so where you had your 10 base 2 coax cable. Obviously what you want to try and do is divide that network up into multiple collision domains. You want to allow as many hosts as possible to start communicating as you can on your network. You don't want just one thing transmitting at a time. So again, if we went back to a simple bus example, that's the easiest way. So you could put a bridge in the middle here. So that would create two collision domains. So these two computers on one side of the bridge, so they could communicate with each other, and if you put that bridge in the middle there, these two machines could then communicate again at the same time, because the bridge in the middle would only pass traffic through it if it saw that this computer here wanted to communicate with somebody on the other side of the bridge. So in this example here, you'd have two collision domains because you've got two separate chunks, but they would be one broadcast domain. So a term that you'll see multiple times going forward when we talk about routing is gateways. So within your router, you could have hard-coded routes, so specific paths that a packet should take based upon its IP address. But obviously you can't think of everything, so you need a default gateway, you need a default route. So if you're not sure where to send the packet, you send it to the default gateway. And at home, you'll see that your router is your default gateway. So in a small office, home office, your Soho networks, your ADSL router will be your default gateway. So all the machines on your network at home, if you look at their routing tables, you'll see that the default gateway is that router. So your home computers will forward their packets across that local network, your home network, to the default gateway, your router, which will then forward them on to the internet. And as we saw with that trace route command, it'll go through multiple hops, multiple routers until it gets to its final destination. Radio demo time, a bit of a show and tell. So in the lecture review session, I'll try and bring along some hardware to show you what a hub switch and a router looks like, so we can play a bit of a guessing game and see what's what. Also in the lecture review session, we'll go through this quick quiz. So as I say, so from those mumbles about what a hub, a switch and a router is, can you identify how many collision domains are and how many broadcast domains there are? And we'll discuss that in the lecture review session. Okay, to show that in action, we can have a look at some of the machines in my home network. Actually, this is a bit of an old picture. Actually, there's more rubbish at home now than there is in these pictures. So what we have is this top machine is acting effectively as a router. Then we have a Proxmox server for virtual machines, and the bottom there we've got a NAS. And my home working machines that I work on that are connected to these servers, again old boxes. So rather than splashing out for the latest and greatest AMD Threadripper, I just run multiple machines. So we have one machine, and then I remote desktop into a second machine to allow me to run all my software. If I am downloading stuff overnight, then obviously I want to turn these off, and I have a small Raspberry Pi that does all my torrenty type downloady stuff in the background. More power efficient, obviously. Well, I suppose this solution is never going to be power efficient, but a little bit more greener. Right, and so for each of these machines we'll have a routing table, and that's what is shown in these diagrams. We've already seen that if you have an IP address that is all zeros in our DHCP example, that is a unknown or invalid IP address or host. But we also see all zeros as the default route in these routing tables. So at the top here we have the routing table for this top machine here. So you can see it's got 5 network interfaces, and each one of those is a NIC, each one of those is a network card. We've got 4, I think there's actually more, I think it's 6 now, gigabit cards and 1 Wi-Fi card, which is also aliased there to effectively give 2 access points, 2 Wi-Fi access points. So the routing table for the Linux box here is given in this screenshot, and you can see it has 2 NICs. One is connected to this machine on the 192.168.30 network, and it's also connected to the Raspberry Pi on the 192.168.0 network. In addition to that, you can see we've also got an additional address here, and we'll chat about that one in a little bit in a later slide. So, okay, these routing tables are used by the various machines to decide where it should send a packet. And the way it does this is that when it receives a packet, it will perform the bitwise AND calculations using these given network masks. And the resulting IP address is compared to the destination IP addresses you see listed here. And obviously these are network IP addresses, not the IP addresses assigned to specific network cards. Remember when we were discussing the special IP addresses, so ending with zeros will be your network address, not a NIC address. And again, ending all ones would be your broadcast address. So what it's trying to do is when you apply this mask, you're trying to match the incoming packet to a particular network. So for example, if say this machine received a packet that was going to this box here, its network interface is 192.168.30.1, and obviously that is on the network IP address 192.168.30.0. So when this receives that packet, it will perform the bitwise AND with the net mask, and they just happen to be all the same on this machine. So what it's doing is it's selecting off the top 24 bits, because remember that's my network ID. So it's trying to match the incoming packet's network ID to something it knows about. So if the first 24 bits are 192.168.30, it knows that it has to shove that packet out on this interface here, as this machine is connected to a switch that joins these machines together for this particular subnet. So the longest match wins. And we'll look at some examples of that one as we go through. But if you can imagine, if we have an IP address that doesn't match any of the listed routes we have here, that doesn't match any of the listed networks we have here, then that network ID will not match. It won't be one of these. It won't be 192.168.1, 10, 20, 30 or 50. In which case, it will match the default gateway. It will match the default route. Because obviously, if you look here, the net mask for the default gateway is all zeros. So if you found anything with all zeros, it's going to be 0. So there's your match. And if that's a match, it will send it, it will forward it onto your ADSL router, which is sitting on the top there. And that will get you access to the internet, obviously, rather than your home network, rather than your local network. So if the destination IP address of the packet received by this machine does not match any of the networks it knows about on its local area network, then those packets will be sent to this IP address. Will be sent to the default gateway. They'll be sent out of this network interface. And this will be the IP address of a port on our default gateway. So also included in this lookup table, you've got some flags and metrics and other things here. So U is for up. U indicates that that network interface is working. G is for gateway. The metric, you can see these ones are here all 0, so they were all treated equally. But down the bottom here, we have something slightly different. So again, we have our routing table now for this PC here. So you can see it knows about a couple of networks. So the 192.168.0 and the 192.168.30 networks. But equally, this machine also needs to know what do I do with a packet that doesn't match any of the networks that I know about. So again, it has a default gateway. So again, net mask is all zeros. So when you perform those net masks, it won't match any of these other networks, but it will match this shortest match here, the all zeros destination, our default gateway. So it'll send it to this IP address. It'll send it to this default gateway. And this IP address is the IP address of the 192.168.30 network interface on this machine. So there's a network card on this machine here with the IP address 192.168.30.254, and that network interface card, that NIC, is acting as the default gateway for the 192.168.30 network. So here we can see we've got some differences to the previous one here. So here our metrics are either 100 or 1000. So with the metric, low is good. So the metric indicates the best route. So the lower the value, the less hops, the faster the communication is. It's an indicator of what route you should take if you have multiple matches. And you can see the logic here. You can see that the 169.254 failed DHCP route has been given a lower priority, a lower metric value, given 1000 compared to 100. So it's less desirable to send stuff down that route. So for any machine, you can see the default routes by running the root command or the IP command. But example here is root -n, and that will give you a listing of each machine's routing tables. You can do that on the Raspberry Pis to see what their routing tables are, for example. So let's have a look at a couple examples. So graphically speaking, this was my network setup at home. So this is the main router. So this router here is this box here. So this is the routing table for that machine. That's my work machine, and that was connected to the Raspberry Pi or via a switch to that main router. So let's go through some examples to see how the packets are routed. So let's look at this first example. So what happens if I'm on this machine? So this machine's IP address is 192.168.30.1. I want to ping the IP address 192.168.0.2, which is the IP address of this Pi connected to that machine. So what it would do is it would look at its routing table. It has to decide where does it send that packet. So the routing table for that machine, as we saw previously, is this. So the destination IP address that we're trying to access, 192.168.0.2, it will apply these masks and then see which is the closest match, which is the longest match. So if you took this IP address and you ANDed it with all zeros, that will produce a 0 result. So that's your shortest match. If you ANDed it with 2552500, you'll select these top 2 decimal digits, and they will be compared to the associated network address. And obviously they do not match at all. So 169.254 will not match 192.168. So that is a non-match. So that's no use. So again, it will use this network mask here to see if this IP address should be forwarded to this interface. So again, if you do the bitwise AND of 255.25250, it will extract the top 3 digits. We can see here. First 2 match perfectly, so 192.168, but obviously the 30 does not match the 0, so that is a non-match. However, if we do the same thing again, using this network mask for this interface, you can see that will extract again the 192.168.0, which matches perfectly the 192.168.0.0 we have here. So the machine knows that it has to send this packet out of this network interface, and that one will send it to the Raspberry Pi, and that's where I want it to go. So everything is good. Let's look at the next one. So now I want to communicate to the machine up here on a different network, on the 10 network. So the 192.168.10.something network. So again, the PC will look at its routing table. It'll do the bitwise AND as we saw previously. It will AND them all, but none of these will match. So none of these 3 will match. Because obviously when we do the bitwise ANDs for the bottom 2, we'll extract 192.168.10. This is the destination IP address I want, and that won't match the 0 or the 30. So none of those are a hit. Obviously this doesn't match because it's not starting with 169. So what you'll have, the shortest match will be to your default gateway, and that is this router in the middle. So this machine here will put out onto this interface, which will send it through to the router will receive it, and it will obviously look to see where it should send it next. So again, it will look at its routing table. So again, it will perform the bitwise AND for each of these interfaces to see if the packet coming in, the destination IP address, matches the network that it needs to get to. So again, if it does that bitwise AND, you can see it's going to be this one. It's going to be the one with the 10 in it that matches. So again, this one will squidge that out onto this network such that it can get to that machine on the 192.168.10 network. Okay, what happens if I want to send a packet onto the internet? What will happen? So this is my ADSL modem. This is my router connected down my phone line to the internet. So I want to get to there eventually. So looking at the routing tables for the PC and this router here, can you see that it will go this way? It will come out of the 192.168.1 network heading towards the router. So go back and look at the routing tables for this machine and this machine. Can you see how it gets through to the internet? Another quiz as well, slightly different one now. Let's say I want to expand my network. Let's say I want to add a new network to this network. So I have a machine here and I add a new network. So I add a new router. So if I'm connecting networks to a network and they are on a different subnet, they are on a different network, then I need a router, because a router connects networks together. So the router connects networks that have different IP addresses together. So now think, okay, what do I need to do? Do I need to add any routing rules to my system to allow a packet from this machine going to 10.0.0.1, so up here, to traverse this network such that it gets through to this machine and obviously back again. I need to get the packet back again to that machine there. So what would you do? Think about the routing rules that would need to exist in these various routers. And as always, we'll have a chat about that one in the lecture review session, and you will be doing this type of operation in the lab, don't worry. Rightio then, so with a little bit of thought and adding specific routing rules to each of our routers, we can get the packets to go in our network to where we want them to go to. So we can use the route command or IP add route. I'll be using both of those in the labs to set up our Raspberry Pi systems. So within our home network, within our Raspberry Pi network in the lab, we use IP addresses that are local IP addresses that are not globally routable, that can't be sent onto the internet. So you think of your machines at home, you may have some network attached storage at NAS, some online file store, may have some media devices, might have a Plex server or printer, things that don't necessarily need to be able to connect to the internet, things that are quite happy to sit on your local network, to sit on your home network. And from one point of view, these are obviously more secure. So if you have an IP address that is only allowed on a local network and not allowed on the internet, it's more difficult to route that one across the internet. So these type of local IP addresses are supported in the IP specification. So what the RFC does, it reserves specific blocks of IP addresses that are for private networks, home networks, that cannot be used on the internet. And the three main blocks. You have your 10, 172 and 192 networks. So you can see here we've got a Class A network. So anything starting with 10.000 will be considered a private IP address, and when you connect to the department's Wi-Fi, for example, you'll connect to a 10 dot network. Equally, the other common one, a Class B one, 192.168.0.0 network, a /16 network, a Class B network. You typically find that one at home. So when you connect to your local router, you will typically be assigned an IP address from that range. And we've got one in the middle there, a 172.16 network as well. So these are IP addresses that you can assign to particular machines because they're not going to be sent across the internet. Obviously, if you do need an internet visible IP address, that would have to be given to you by your ISP, by IANA. Obviously, you just can't choose any old IP address because it may be already assigned to a company, another institution. But these ones here are on your local network, so you can go to town on those, assign those to any machine you desire. In addition to that, as we looked at in lecture 2B, when we looked at DHCP, we also have a self-assigned IP address. So if a DHCP request fails, you can self-assign an IP address on the 169.254 network, a Class B network there. And as we discussed, as a pseudo-random number will be allocated by yourself, the lower 16, to give you an IP address. But all four of these IP address ranges will not be routed out onto the internet. So if you were to send those to your ADSL modem, they would be dropped. These are local IP addresses only. Obviously, this now raises a question. So when I connect to the department's Wi-Fi on the 10 dot network, or when I connect to the local area network at home on the 192 network, I may want those machines to access web resources. I may want to access a web page. So how do I go from a private IP address to a visible IP address to a internet routable IP address? And the way to do that is via NATing, or network address translation. There's a few different flavors. They can be static, dynamic, or based on ports, but we're going to go through a typical example here, sometimes called IP masquerading or IP overloading. So the trick here is that your router will maintain a table of IP addresses and ports, source and destination ports, because those are what define a connection between two machines. Remember, right at the beginning we said, what defines a connection between two machines? Well, it'll be two IP addresses, your source and destination IP address, and the source and destination ports. And if you know those, you can uniquely identify every connection. And knowing that, we can do a little bit of trickery on each of the routers to allow us to replace one IP address, to replace our private IP address with a internet routable IP address. And fingers crossed, touch wood, this diagram will help explain that. So this network diagram here is for my home network. So we have my home router, my local area router, made up of those 6 Ethernet cards, that top rack in that 19-inch rack system. And like you, I have an ADSL modem connected to my phone line for my internet connection. So I actually have a double NATed system, just showing off. Not really, it's just easy to set up. But to break this one down, the first thing we'll consider is just the ADSL modem. So we'll consider connected to that across a copper wire is a PC, and that PC has an IP address of 192.168.1.70. So that would be given out by your DHCP server running on your ADSL modem. So this modem itself will have a DHCP client which will connect to your ISP across the internet. So it will be given a internet routable IP address from your ISP, PlusNet, BT, whatever it may be. And in this particular case, it's the IP version 4 IP address 81.34.21.1. We can imagine a scenario where we've got a computer connected to this network, on this network, and it wants to open up a web page on a remote server. So it's going to be using the HTTP protocol, and it'll be sending out a packet to port 80 on the remote server. And that remote server will have an IP address. And for the purposes of the example, I'm going to take that as 216.58.213.3. So if you can imagine that connection, it'll be made up of 2 IP addresses and 2 ports. So this is what is shown here. So I have my source IP address. So that'll be on my local network. That'll be a 192 network, and a remote IP address, the IP address of that web server out on the internet. We know the port where I want to connect to. All web servers, I will connect to port 80. And my local port, well, that'll be a dynamic port, a ethereal port, one that my machine has allocated from that pool. So in this particular case, 3204. So again, your PC will look at the destination IP address. It goes, oh, I can't find that on my local network, so I'll send it to the default gateway. And the default gateway, obviously, is the ADSL modem. So it will receive that, and it knows that it can't put out that packet onto the internet because it's got a 192.168 IP address. So it knows it has to replace that with its publicly visible IP address. So it maintains this NAT table. So it has that packet coming in, so it'll replace that IP address with its internet visible IP address and replace the port with, again, the next free port number for its network connection coming out here. Obviously, it won't affect the destination IP address and port because that's all perfectly fine. All it's done is replaced this block here with this block here. So when a packet comes back from the web server, if it has this destination IP address and this destination port, then it knows it can look that up in its lookup table, in its NAT table, and replace those with the associated entries. So replace that IP address with one that is on your local network and the port that that PC has assigned for this connection. So you convert it back to its original form. So now when that packet is placed onto the network, it will be routed obviously to that machine. And that's what you'll have on your typical home machine. But because I've got an additional router in here, so this IP address is not an IP address of a PC, it's the IP address of this network port on my router. So again, to convert this IP address that was given by the DHCP server in my ADSL modem to the router also uses network address translation. It will also have a NAT table, which will convert the 192.168.10 networks, the 20, the 30, the 40, the 50s, and the 60 subnets into a 192.168.1 network. So exactly the same process here. So a double natted network. I would say that was a very good way of doing it or a very common way of doing it, but it's the way I did it because my router was very naff. So it didn't allow me to set up any specific routing rules within it. It's a very vanilla router. So to get around this one, it was easier to take this approach because it was all just auto-connected. It was all very easy to set up. So to see the complete journey, so let's imagine I have a PC that is in my office. So that will have an IP address on the 192.168.30 network. So let's say it's 192.168.30.5. It wants to open up the connection to that web server over here. So again, this is our starting point now. So the source address will be the IP address of this machine. So it's on the 30 network. And again, it will assign that a port, and the destination again is just the same, going to that server on port 80. So that packet will be routed to the router. It knows that it has to forward it onto the 192.168.1.0 network. So it will do that network translation. So the ADSL modem is our default gateway. So that will have an IP address of 192.168.1.254. The router has been assigned an IP address 192.168.1.70. So this router here will do this network address translation. So from the 192.168.30.5 IP address, port 1055, it will change that to 192.168.1.70. So the IP address of its connection, and assign it the next free port, which in this particular case is 3204. So you can see that top line has been replaced. That packet will then be forwarded to the default gateway, which is your ADSL modem again, and it'll go through exactly as I previously described. Again, it will replace that top line you can see there with the 81.34.21.1 IP address, and again the next free port that it has, and then that will be passed onto the network, and it'll come back again, get translated once, get translated again, and finally it'll get back to our PC. So NATing, a great way of reducing the number of IP addresses you need if you want to connect more machines to the internet. And that's one way we used to extend the life of IP version 4. So you can imagine all the machines in your house, however many that may be, the television, the printer, all those machines will have a local IP address within the house, and by using NATing they can all share the one internet routable IP address. So it means that all your machines inside your house don't need to have an internet routable IP address. They can all share just the one that your ISP has given you. So greatly improving the efficiency there. Unless you want to make a direct connection into that network. So if you want to connect, I don't know, from the university back into your home network, having a NATed network does add complexities. And you may have done that if you have your own game servers, etc. So opening ports, port forwarding to allow you to pass through connections to the right machine can be a bit tricky. But that's going slightly off topic. But hopefully this diagram helps explain the principles of NATing, network address translation. So by considering the things we've looked at so far, we've seen that all our routing need to have routing tables. So they have to be able to work out how to calculate where they have to send a packet onto the next hop by using that net mask and matching it to the associated network IP address. We also know that our routers are store and forward devices. So we send a packet to that router, it has to be buffered on there and then forwarded on to the next hop in our packet switch network. So conceptually we know what a router does, but how does it do it behind the scenes? What's inside that black box? Well, I'll try to break that one down into this block diagram you can see here. So the thing to remember, obviously you'll have multiple ports on your router. So each one of those you can think of as a independent piece of hardware, all working in parallel, all capturing incoming packets and then buffering that data into their local queue, into the local receive buffer. So that's what we got going on here. So here graphically are our bits coming in to our system. So our layer 1 standards for our copper or fiber cables. Obviously that will need some digital signal processing, some filtering to extract those ones and zeros. But eventually you'll start to receive them and you dump those into your input queue. So remember, with your switches and your routers, it's a store and forward device. That means you have to receive the whole packet first, and then obviously you check the checksums to make sure there's no errors in that data you've received. And then from that, you need to extract the IP address, or the MAC address if it's a switch, to work out where that packet needs to go next. So obviously here we're working with layer 3 devices, so we're looking at IP addresses, so we read in that packet, and if all the checksums pass, we need to look at that IP address to work out what port we need to forward it out of. Where is that packet going next? What network does that packet go to? Remember the key difference between routers and switches. A router is looking to transfer your packet onto the next hop, whereas a switch, which we'll look at later, is interested in moving packets around your local area network. Another thing to remember is that there's some processing involved in this. Remember, we said that every time a packet goes through a router, the time to live value is decremented by 1, so that will change the values in the IP header. So if the values change, then you will need to recalculate that checksum, and all of that is done within your router. So don't think of a router as just a passive device, if that makes sense. It's actively making decisions on whether packets should be dropped because they are corrupted, updating those headers within the packets, and then moving them to the correct output port. So again, like the other examples we looked at in the previous slides, the router will have a routing table. It'll have a list of rules, that is net masks and network IP addresses, and from that it will work out where each packet needs to go next. Now, as you can imagine, these packets are coming in at scary speeds. So typically today you're looking at gigabit links. packets, so 1,000 million bits per second. So you don't have long to perform all those calculations, decide where the packet goes next, as eventually your input queue will become full. That is, if you don't shift the data out faster than it's coming in, your buffer will max out, there'll be no more space, so the incoming data, it will be just dropped. So those packets will need to be retransmitted. So it's important that you can process these packets with minimal delays. So to speed some of that up, we tend to use contents addressable memory, so CAM, as it says down the bottom there. And basically what this allows us to do is parallel searches. So if you were using your normal DRAM memory or SRAM memory, then you'd access that memory sequentially. You'd read each memory location in turn, and then using that data to determine what is the correct destination for this packet. By using contents addressable memory, you can search that memory in parallel. You can define a search key, you can define a mask, you can do the type of operations you want to, not sequentially, but in parallel. So that's what you typically see in these routing devices. These forwarding decisions are accelerated by using this type of memory. Now that's all well and good when you've got those routes kind of defined in a routing table, but the router will also gain knowledge about different routes from other routers using routing protocols, OSPF and RIP, for example. We'll look at RIP in labs. That's a nice easy one to kind of get you started on routing protocols. So protocols that transfer information about routes between routers. So that is an application layer protocol. So to process those packets, we need a routing processor. We need something at the transport layer and the application layer to allow it to extract those routes. And then it will offload that information into our CAM memory when it has received updates to its routing table. But as I say, to speed things up, obviously we don't want a significant software layer processing our packets within our router. We want everything really to be hard-coded in application-specific hardware because of the high data rates that we are dealing with. So eventually, either controlled by the routing processor or the dedicated hardware will identify what output port that packet needs to go to, what network that packet needs to go to on its next hop to get to its final destination. So to do that one, we have to connect the inputs to the outputs, so our input ports to our output ports, and to do that we have a crossbar switch. We'll need some sort of switching matrix, and that can be done in a number of different ways. So it can be just simply shared memory. Obviously that will introduce some sequential element to the behavior of our circuits. So if you have just one memory device that stores all your input and output port queues, then when you're transferring that data from one input queue to one output queue, then all the other ports can't use that hardware. If you've only got one memory device, only one memory transaction at a time may be allowed. In which case, all the other input and output ports will have to wait, which will hit your performance. Alternatively, if you want to maximize with speed, then you'd use some sort of switching matrix crossbar switch, as I've sort of illustrated here in this diagram. So within your router, you'll have a number of communication paths, and this will allow you to switch different input sources and different output sources onto and off these communication links. So for example, if my input data is coming in on this input port, and I've identified through my routing tables, through my dedicated hardware, that it needs to go to this output port, then I can look for the next free communication channel. It doesn't have to be this one, it could be a different one. I connect my input port to it, I connect my output port to the same channel, and then I can stream the data through that link to the output port. And because I have multiple internal communication links, whilst that is going on, another device can connect to a different channel and stream its data to another output port. So again, parallelism, allowing us to maximize performance. So these communication links, you can think of the same as circuit switching. So an input port here is pushing data onto that communication link. It's being used. No one else can use it until that transfer is complete. So if you don't have enough communication channels within your system, again, you'll have another bottleneck. So if an input device can't connect to a communication channel because they're all being used, then again, you'll start to drop data. You'll start to drop packets, because there's no space perhaps for the data coming in on a particular port. However, if the world is good and you're not maxing out your router, fingers crossed, touch wood, you've got enough capacity, you have enough spare space, so your packet will be transferred to the correct output port. And again, obviously that'll be queued, waiting to be transmitted, and then just like the input port, our output port is a separate parallel piece of hardware. So each of these output ports are working in parallel together, outputting their stored packets out onto their associated network. So things to take away from that diagram, we can see that the router is fully duplex in the sense that it can receive and transmit packets at the same time. And that means that our input data and our output data are going across different wires. And we'll see that later when we get down to layer 1. We'll see that we transmit and receive across different pairs of twisted wires. That means we can't get collisions in the sense of 10 base 2. So we're not transmitting and receiving data onto the same physical wire, but we can still drop packets. We have a finite amount of memory in our input and output queues and a limited number of communication links between them. And owing to these limitations and these shared resources, that means there's a possibility we could run out of space in these queues. And as a result, if more data comes in and we've got nowhere to store it, the router will just start to drop those packets, which is equivalent to our old-fashioned collisions in the sense that the transmitting host will need to retransmit those packets. All right, a quick quiz. Quick answer questions, hopefully. So, inside your router, what type of communication network do you have? Is it circuit switched or packet switch? So, inside the actual router. Obviously, the router itself is a packet switch device. If you have 10 gigabits per second links coming into your device, and each packet is 64 bytes, so the minimum specified size, how long do I have to determine what is the correct output port? So how long do I have before the next packet coming in has been received and needs processing? So I'm receiving multiple 64-byte packets at 10 gigabits per second. When I've received one of the packets, it can be processed. Whilst I'm processing that packet, obviously I can be receiving the next one. So how long do I have before trouble starts to happen and I start to get a backup, a queue, a bottleneck? And if that does happen, the final question there, what happens if I can't process the packets fast enough? So I have too many packets coming in too quickly. What will the router do? So what to take away from this lecture? So fingers crossed, touch wood. You've identified here at layer 3, our network layer, that everything's IP addresses. So stuff gets moved around the network based on IP addresses. So each host is identified by an IP address. And the routers that move our IP packets between the network of networks, that is the internet, make those decisions based upon those IP addresses. And obviously the hosts and our routers within our system perform those operations using their routing tables. As you may have spotted, as always, we've glossed over some bits of our networking packets. So we looked at, basically in this one here, the source and destination addresses and the net masks. But within that IP header, you've also got some other fields. So we've seen TTL before, so time to live, but we'll look at that in a little bit more detail. What does that mean? And fragmentation fields, that's a big old section there. How do we break down bigger transport layer segments, TCP, UDP segments, into smaller IP packets? Because as we discussed, the packet size across your network is determined by your MTU. And just like DHCP, we saw that we could, if we wanted to, manually configure the IP addresses for all our hosts on our network, but that's too much fun, so we used the DHCP protocol. Exactly the same for routing tables. We could manually enter all the routing rules for all our routers manually, but that would be too much fun, so we need protocols to do that for us automatically. And that's what we'll look at in the next set of lecture slides. So, as always, that's where I will leave it, and we'll continue this journey next week.